Hi, welcome to this class. Here we will be talking about electron beam evaporation. Now, what we have seen? We have seen that there are physical vapor deposition technique. In physical vapor deposition technique, you have thermal evaporation technique, you have ebeam evaporation technique, and you have sputtering. Right. Now, thermal evaporation we have already seen in the last lab class, right, how actually things operates, how the equipment looks like, how you can create a vacuum, right, what is a base vacuum, what is a high vacuum, how to apply the voltage to the boat or the source holder, how to load the source material onto the source holder, how to load the substrate on the substrate holder, right. When you heat this boat, the material that is loaded onto the boat will get melted. When it gets melted, it gets vaporized, evaporates, and then it gets deposited onto the substrate. The difficulty with thermal evaporation is, or the limitation is, that if the source material temperature, the melting point, the source material melting point is higher than the source material, that is source holder itself. The material that is we want to evaporate, its melting point, if it is higher than the source holder material itself, then thermal evaporation cannot be used. In that case, we have an alternative technique, and that alternative technique is called electron beam evaporation. Electron beam evaporation, we have seen that in the theory class, that how the electron beam is generated right from the filament, how it is accelerated through the accelerating electrode, how it is bent through the magnetic field, right, and how it is incident onto the source material. In this case, we had a crucible, right, and on crucible either you can have a point source or you can have a raster scanning. Now, with this technique, we are not really heating the crucible, but we are melting the material by using the electron beam. Electron beam will heat the material that is loaded onto the crucible, and this molten material will vaporize and it will get deposited onto the substrate. So, let us now see in the lab class how this electron beam evaporation system works. How can we create a base vacuum with primary pump, how we can create a high vacuum with a secondary pump, right, what are the panning gauges, Pirani gauges, substrate holder, source, the crucible, right, and how we can generate an electron beam. Actually, you cannot see the electron beam because it is all covered, and then at the end of this one, what you will understand is that it overcomes the limitation of the thermal evaporation. Now, there is another technique which is sputtering, that also we have recorded, right. So, first let us see how the electron beam evaporation works.
Hello and welcome to this demonstration of e-beam deposition. So in the coursework, Professor might have already discussed about physical vapor deposition, and even before that he might have talked about the basic steps of micro and nano fabrication, in which deposition is one of the crucial steps. Now this deposition can be of various types, and the most common are PVD, that is the physical vapor deposition, and CVD, that is the chemical vapor deposition. Now what I have here with me is a tool that we use for PVD, for physical vapor deposition, and this tool is capable of two types of deposition. That one is thermal based deposition, wherein the source material is heated using resistive heating or Joule heating. Basically, in that case, what we do is through a wire we pass some current, and as the wire starts heating, it will melt my material, and after melting it will start evaporating. This source material will evaporate and get deposited. Now another option in this tool is the e-beam evaporation. So what happens in this case is, I have a source material in a carbon crucible, graphite crucible, sorry, and an electron beam will come and hit my source material. Now, because of this high kinetic energy of the electrons, it will be converted into heat, and it will start melting off my source material. Once it starts melting off at a given, if the given conditions, atmosphere, the conditions such as the vacuum, that is the pressure and the temperature are sufficient enough, it will start evaporating, and these vapors, these source material vapors, will go and settle down on my substrate, and that's how I'll get my deposition. Now that was the theory part in a very brief. We'll today see how this tool actually works. So we'll be having a demonstration of the e-beam evaporation, like I said. So let's start with this tool. First, I'll switch it on. Now, once the display comes, I'll click on the hardware reset, and you can see the safety interlocks are on. That means all the doors of my tool are properly closed, and also my system is under vacuum. Okay. So now you can see there is the water cooling option. That means the water cooling is happening properly, and the source enable is off right now. Basically, the source is the source for the electron beam, which is off right now. And once the deposition starts, it will start glowing. Now we can see here this panel. Okay, this is the panel which also acts as a display as well as input. So at this interface, we can see the system status is standby. That means my pumps are not running, nothing is running right now. It is just sitting idle. Okay, now I have two options here. One is start and one is vent. There are multiple options, but the options which are available to me are start and vent. So here what start means, I'll start the pumps. So we'll see that there are two kind of pumps in a short while. And there is this vent. Vent means right now my chamber is in evacuated conditions. When I press on vent, atmospheric gases will start going in, and it will come to an atmospheric pressure, and I'll be able to open the door of my chamber. Right now, since it is in vacuum, there will be a lot of pressure. It is not possible to open the door. So I'll just click on start. Now the pumps will start running, and meanwhile we'll see what all options we have here. Let's have a closer look at the options that we have on this panel. So we already discussed that there is the main power switch, the safety interlocks, the water cooling indicator, and the source indicator. Now if you can see here in this panel, the system status right now shows turbo pump is ready. That is one of the pumps that we will be using. And the chamber pressure is it is in vacuum, but it is just merely like 10 to the power minus 2 millibars. It is not really the kind of pressure in which we can carry out the deposition. So initially we had start and vent options. Now we have start, stop, cycle, vent, and process. So one by one we'll see what each of these options will do. Like I said, the start, when you click on start, the pumps, both the pumps, so we have two kind of pumps. One is a roughing pump and another one is the turbomolecular pump. Okay, so what does the roughing pump do? It takes the pressure from atmospheric pressure to around 10 to the power minus 3 millibar, and then the turbomolecular pump comes into action, and it takes the pressure from 10 to the power minus 3 millibar to further till 10 to the power minus 6 millibar, where we actually carry out our deposition. Okay, now coming back here again, we have stop. So when we click on start, both the pumps start running. Then we have stop, that is to stop both the pumps. Then we have cycle. So right now what is happening is our pumps are running, but they are not connected to my chamber. So my chamber is still at the same vacuum condition, and it is not right now it is not connected to the pumps. So once I press on cycle, the evacuation process will start, and then we have our vent option. Okay. So if I click on vent, like I said, atmospheric gases will go in, and I'll be able to open the door. So apart from that, we also have here process, which we will use once the vacuum condition has reached and we are ready to turn on our electron beam. Okay. So for now, we will vent it out. But meanwhile, let's also see what other options, what other analog options we have here with the new so many buttons. So if you can see here, there is the source control first. Okay, so there is the on off. This gives the power to the source, that is the electron beam. So when we are talking about source, we can here the source doesn't mean the source material which we are depositing, but rather it means the electron beam source. You can see EB3 source. So there are some indicators like power, which indicates that there is power to the electron beam, electron gun. Then there is vacuum. If the vacuum is not reached, the electron gun won't operate. So there is this indicator for vacuum. Then we have water, that is the cooling water, and etc. etc. So here we have the first is on off, which gives the power to the transformer or this unit which operates the gun. Then we have the actual power to the gun. Once you press that, then only there will be a voltage applied to the gun. Otherwise, it will just show 0 kV and 0 milliamps. Okay. Then after that, we have here the knob for controlling the how much current we are giving to the electron beam. Okay, then we have this EB3 sweep control. So basically what happens is when the electron beam is hitting your source material, it will be at a single point, but there is an option to sweep it or rather raster it. So in that case, what will happen is the beam will slightly move in X as well as Y direction. So what happens due to this is, rather than only the heating taking place only at a single point, what happens is a larger area is covered and we get a more uniform heating. So for that we have the sweep control, where we have the control for X and Y direction amplitude. These two knobs are for controlling the amplitude, that is from the mean position, how much till extreme it will go, how much it will go in X direction and how much it will go in Y direction. Then we have this this switch, which is a binary switch, basically 0 and 1. 0 means that it is a point source and 1 means that it has started sweeping. And then we also have the control for the waveform in both X and Y direction. We have usually we have 2-3 options, but usually we use a sinusoidal because it is basically quite smooth. When you talk about sinusoidal, it is a very smooth motion that it goes to the extremities at a very slow speed, then comes back at the maximum speed and slows down again. So that is a very smooth motion, like if you might be familiar with a simple harmonic motion, or basically a movement of a spring and mass. So because it is a very smooth transition, we prefer to use a sinusoidal waveform. So at the extreme right, we have the panel for the turret controller. So like we will see that there are 4 slots, as in at a time I can load 4 materials in my chamber. So in each of these slots I can put a graphite crucible. So right now I have 4 such crucibles loaded into the chamber. In the first slot I have titanium, in the second slot I have gold, in the third I have platinum, and in the fourth slot I have aluminum. So in order to operate this turret, I'll have to click on this switch on, and then using this knob I can select whichever material I want. I can switch between the 4 materials. And here this knob you can see is to control the speed of this turret. Okay, right now we have kept it at the maximum position. And next we have is here the DTM, or the digital thickness monitor. Okay, so when we are depositing, we must also know whether the deposition is taking place or not. Sometimes it may happen that due to some malfunction, you carry out the entire process, but the deposition is not happening. And in some cases, you also need to have an estimate of how much thickness you have got. So that's why we use this thickness monitor. So how this works is, inside there is a quartz crystal, and that is why this DTM, digital thickness monitor, is also sometimes referred to as QCM, that is the quartz crystal monitor. So basically there is a quartz crystal which is suspended near the source or in the chamber. So what happens is, it has a particular resonant frequency. But when you keep on adding some mass, because whenever the deposition is happening, there will be some material getting coated on this quartz crystal. So what happens is, due to this extra material, extra thickness of material, there will be a change in mass, or rather an increase in the mass of this crystal. Due to this increase in mass, there will be a slight change or slight shift in its resonant frequency. Now, if you can calculate somehow this shift in the resonant frequency, you can have an estimate of how much mass is being deposited, and that's what this digital thickness monitor does. So if we know how, since this crystal we know exactly how much area there is on which my material will be deposited, and thickness is something we need to find out. And if we exactly know what is the density of this material which we are depositing, we can easily calculate what is the thickness. Okay, so that's about the DTM. Then we have some other options as well. On the left here, we have something for the thermal deposition. So we won't be focusing on that, but we'll rather see what's on the right. These 5 knobs, what do they do? The first one is for the DTM. This is when you switch it on, the digital thickness monitor starts. Okay, then there is a ebeam gun shutter. So if you turn it on, so there is a shutter. When we open the chamber, we'll see there is a shutter which is on top of my source material. So the function of this shutter is that once we heat the material, okay, and like I said, this material needs to be heated at a particular temperature in a specific favorable vacuum. Only then it will start evaporating. So this heating which I am doing right now using an electron beam, it cannot be very sudden. Slowly and steadily it will start heating. So it is possible that initially, as soon as you start heating, there will be some vapor coming out, but you don't know exactly how much it is. Okay, and you cannot predict accurately what will be the rate of deposition. Okay, so what I'll do meanwhile, when my this material is getting heated slowly, I'll have a shutter or a cover which will be on top of this on top of this crucible. So what happens is, unless and until my crucible or my material is sufficiently heated that I know exactly now the deposition is going to start, I'll keep this shutter on. So whatever irregular deposition is going to happen, it will only happen on the back or the bottom side of my shutter, and it will not actually affect my sample or the substrate. Okay, so basically, and one more function is, as soon as I want to stop my deposition, the idea would be to reduce the current. But even if I reduce the current very quickly, which is not advisable, there will be my material is still heated, and it will slowly a little bit of material will still be coming out in the form of vapors, which will still keep on depositing. So how do I have an accurate or precise control or for how much time do I want to deposit? So again, as soon as my time is done, like let's say I'm depositing for 5 minutes, as soon as my stopwatch hits the 5-minute mark, I'll turn off this shutter. So again what will happen, even if some vapors are coming out, because it is not cooled down properly, my shutter will come and stop the deposition on my sample. Okay, now we have here something called as the rotary drive. Okay, so when we see the chamber, you will see there is a substrate holder, and at some locations I will have my sample. Okay, so what happens is, it is possible that at some location, let's say which is further from my source, there will be the deposition might be a little less, and at a position which is directly above my source, material source, the deposition might be higher. So what I'll do, I have this option of a rotary drive. So what happens is, my substrate holder starts rotating, and this ensures that there is a uniform deposition for whatever time I am depositing. Okay, and here now I have this knob using which I can actually control the speed of the rotation. Like right now I have kept it at 3 RPM, but depending upon my requirements, I can go up to like let's say 5 RPM or even less, 1 RPM. Okay, I'll stop it again. And now it's time to see what's inside the chamber. Okay, so for that what I'll do, I'll just click on vent, and you will see, you might be able to observe there is a slight hissing sound, which means that the air is going inside the chamber. And once this hissing sound stops, that will indicate that my chamber has reached the atmospheric pressure, and it is possible now for me to open the door. Otherwise, what will happen, because of this atmospheric difference, outside it is 10 to the power plus 3 millibar, inside it is 10 to the power minus 2 or minus 3 millibar at this moment. There is a huge pressure difference, and which demands that I need to have a very large force to open the door. Okay, once this this chamber comes to atmospheric pressure, we'll open the door and see what's inside. Now the hissing sound has stopped, and we can see in the panel that the atmospheric pressure has been reached. That means now it is safe to open the chamber door. And now we'll have a quick look inside. What do we have? The first and foremost is the substrate holder, which I'll just remove. And now we can have a look inside of what all things we have. The first is the spindle on which my substrate holder will be mounted. And like I said, it is a rotating, it has a rotation drive, because of which which I use for having a uniform deposition. So if you can turn this on. Okay, once you switch on the rotary drive, this spindle starts rotating at right now it is set at 3 rpm. We can switch it off. Now here I have this this block, which is actually the heart of this this ebeam deposition system. In this we have so in this we have the first here is we have the filament. And what happens is the electron gun or the filament ejects electrons, which is directed in a sort of a circular fashion from this port to the material holder or the source holder here. So here we have the shutter, ebeam gun shutter, which I sorry, not ebeam gun shutter, but yeah, the shutter which we use to control the deposition time. Okay, if you can switch it on. Okay, now the shutter has moved, and here I can see there is a crucible in which right now I have aluminum. So like I said, there are 4 slots. I can switch in between these 4 slots. So here you can see, if you can see, there is a sort of a chain drive which controls my turret. If now what I'll do is I'll just show you one of the crucibles. Using a tweezer, I'll just carefully lift it off, and this is a graphite crucible, and inside you can see the shiny material, which is aluminum. And it's not in the form of pellets because we have used it for some depositions, and it has melted and stuck to the sides. Okay, I'll carefully place it back. Okay, and I'll close back my shutter. So these are the main components of my deposition, the e-beam deposition. But you will also see there are some extra hanging structures. So this is the holder for the quartz crystal. We have one here as well as one here. One is for the electron beam deposition, e-beam deposition, and one we have for the thermal deposition. It is calibrated in such a way. So, and here we can see there are there is some other attachment which is covered in aluminum foil. That is the setup for the thermal deposition, which is not in the scope of this discussion today. So now we have that. Now I'll show you how to place the sample on the substrate holder, and we'll attach it back to the spindle. So here we have our substrate holder, which I took it out from the chamber, and here I have a glass slide which is completely transparent, and on this we'll be today depositing aluminum. And aluminum we have in the crucible number 4. So for that I'll just place my glass slide in this region, and using these screws and holders I'll secure my sample in place. Otherwise, when if it is not secured in place, as soon as I try to attach this substrate holder back to the spindle, my sample will fall off. So I'll just carefully use these holders, and using this Allen key I'll secure it. Same thing here. And now using a tweezer I'll just try to push and see if it is secured or not. Okay, since my sample is now secured, now it is time to load it back into the chamber. Now as you can see, we have attached this glass slide and secured it using these holders and Allen screws. Now it's time to load it into the chamber, and we will start the evacuation process. Now that's the reason we had to secure it, because when we keep it upside down, the sample should not fall into the chamber. Now I'll just quickly show you when we turn on the rotary drive, it starts rotating. This is more evident rather than just seeing the spindle. Okay, now I'll just close the chamber. And before that, whenever you are depositing, it is a good idea that you can actually see inside what's happening inside. So for that we have this viewport. Basically it's a glass, and on the opposite side we have this metal shutter. Okay, so the idea is whenever you want to see inside the chamber, you pull this lever and see what's inside, and as soon as you are done, just close it back. So this ensures that if it is constantly open, what will happen is whatever material you are depositing on your samples would also get deposited on this viewport glass, and it is really difficult to replace or clean it. So I'll just lock my door, and here you can see we have 3 options available to us: the cycling, process and sealing. So what will happen is process is when we want to start the deposition. Okay, but right now it won't be possible because our chamber is not at vacuum condition, rather it's at atmospheric pressure. And another option is to seal, but we won't be using that option here. What we need to do here is start the evacuation process. That is, here we have the cycling. So once I click on it, so basically what will happen right now, you can see the pump running. So my roughing pump or the main pump has started. So now it will take the pressure from the atmospheric pressure, that is 10 to the power plus 3 millibar, to somewhere around 10 to the power minus 2 or minus 3 millibar. And once that happens, my turbomolecular pump will kick in, and it will take it to further 10 to the power minus 6 millibar, where we will actually start our deposition. So let's quickly go to this mimic diagram and see the system view. Okay, now we'll have a closer look here and see exactly how the schematic of this this tool looks like. So in this display now you can see the mimic diagram. Okay, so here the first rectangle on the top you see is actually the representation of your chamber. Okay, and now this chamber is directly connected to this line, which is connected to your roughing pump. So what happens is, right now this is your turbomolecular pump and this is your roughing pump, and you just saw that this valve was initially on. So what and this valve was off. So what happened was the roughing pump was directly connected to my chamber as the pressure was reaching from 10 to the power plus 3 to and approaching 10 to the power minus 2. As soon as it reached 10 to the power minus 2, what happened was this valve turned off, and so that my chamber, which was earlier connected directly to the roughing pump, this line got disconnected, and now it is running through this high vacuum valve is open, which is connected to your turbomolecular pump, and which is further connected to the backing valve, and from through the backing valve it is connected to the roughing pump. So right now it is the pumps are working in series. So wherein my chamber is connected to the turbomolecular pump, and which is further connected to my roughing pump. So the pressure goes down like this. Here it is. Here we have atmospheric pressure 10 to the power plus 3. Here it goes somewhere on this side. It reaches somewhere 10 to the power minus 2 or 10 to the power minus 3, and then through this turbomolecular pump here in the chamber we have an order of 10 to the power minus 3 millibar. So and also we have various accessories, such as here we have the pressure indicator, then interlock status, and we have some other valves as well. So that's the entire gist of this representation diagram of our tool. So now let's get back to the system control, where you can see what is actually happening here. We have the cycling sequence, that is the fine pumping is going on. Earlier we saw that it was rough pumping. So wherein my pressure was approaching 10 to the power minus 2 or minus 3. Now that stage has crossed, and we are in the fine pumping region, where the turbomolecular pump has kicked into action. And right now options that we have left are seal and vent. So now once this fine pumping is complete, that is the pressure has reached somewhere near 10 to the power minus 6 millibar or somewhere nearby. So in that case we will be able to start our deposition. Okay, so we'll wait till the desired pressure is reached, and then we'll continue with the process. So now the vacuum has reached where we want it to be, which is in the order of 10 to the power minus 5 and 10 to the power minus 6 millibars. So what we'll do is now, as we have already discussed, that when a sufficient vacuum is reached, the mean free path of the particles increases, which means that basically the particles which are coming out from your source will reach your substrate with minimum collisions, which ensures that there is enough kinetic energy left with the particles when they are about to be deposited on your sample. Okay, so now since the vacuum has reached, we will turn on the e-beam. I have switched on the main supply for the e-beam. Now I'll turn on the transformer here. And finally I'll turn on the power. Also, what I'll do is I'll put this system in the process mode. For that, first I'll need to seal. And once the chamber is sealed, I'll click on process. So it shows that the system status shows that the process sequence is pumping down. So once this is ready, okay, now we can see that the pump down sequence is on. The throttle pumping is done. Now we will start the turn on the power for the electron beam gun. So you can see here there is some display coming. So the first display, LED display, shows you the kV, how much kV is supplied to the e-beam or the e-beam gun, and the second one shows the current which it is drawing. So now since the power is on, the vacuum has reached, I'll turn on the gun. And if you can see here, we have a voltage of 5 kV. And now the next process would be to slowly increase the current for the gun, and that's how the power will be delivered. Okay, so before that, there are certain pre-checks I need to ensure. First is the I need to make sure that which crucible I am using. For example, today we are going to be depositing aluminum on a glass slide. So I need to make sure that here in the turret, which has 4 slots, that means at a time in our chamber we can load 4 different materials, and the materials which we have available with us are titanium in crucible number 1, gold in crucible number 2, platinum in crucible number 3, and finally aluminum, which we are going to deposit in crucible number 4. So if you can see here, I have set the crucible number 4. Okay, so that's what is going to be deposited. Okay, now what we'll do, slowly I'll start increasing the current. Okay, so once the what happens when I'm increasing the current, the electron beam, which is it travels from the source, the gun, and follows a sort of a circular path and falls on my source material. In this case, we have aluminum in a crucible. So when this electron beam would fall on my crucible, it will start melting off, and that's how the vapors will travel. Since we have a very good vacuum now, the mean free path is sufficient, so the vapors of aluminum will come without any collisions, will come to the substrate and get deposited on the sample. Okay, so the SOP says that we cannot heat any material with a very large current because there will be a thermal shock. So what we'll do, the deposition, as we know, it takes place at around 35 milliamps at a voltage of 5 kV. Okay, so we cannot give 35 milliamps in one go. So what we'll do, in steps of 30 seconds and 1 minute, we will go from 10 milliamps, 20 milliamps, 30 milliamps, and 35 milliamps. So let's get started. So I'll just increase the current here first. Okay, so now I have 10 milliamps and I'm starting the stopwatch. As soon as it reaches 30 milliamps, 30 seconds, I'll increase it to 20 milliamps. Okay, so it ensures that whatever material I have, it slowly and gradually it is getting heated up. Okay, so we are almost there, and I can also see actually that there is some glow because of the electron beam. There will be some glow, some yellowish glow, which we will show you. Now since the 30 seconds are done, I'll increase it to 20 milliamps approximately, and once 30 seconds are over, I'll increase it to 30 milliamps. So now let's increase the current further, and we have 38 milliamps. So once the metal is like well heated, if you can see it from the viewport, it will have a red hot appearance. That means that the evaporation has started. That is a good indication actually. And also once the preheating is done, then we will open the this shutter, and the deposition will start happening on the on your actual sample. So as we have discussed that there is a shutter on the source material. So when the e-beam is the electron beam is coming and the shutter is closed, all the deposition will be happening on the shutter. So this ensures that you have a proper control over the deposition rate or the deposition time. As soon as you open the shutter, that's when your deposition on your sample will start, and to stop the deposition, you will close the shutter. Now we have 30 milliamps for 1 minute. We will be increasing it to 35 and 35. Great. So So as I was saying, we'll open the shutter and the deposition will start. So at 35 milliamps, I'll keep it for 1 more minute, and I'll open the shutter. Meanwhile, we'll see what else do we have. There is the digital thickness monitor. I'll turn it on. Okay. And we have the shutter here, and also for a uniform deposition we need to have a rotation of the sample. So there, like we saw the chuck, it is a rotating chuck. When we place our samples, during deposition we turn on the rotation, so it ensures that basically the deposition which we are having will be uniform. So I'll turn on the rotation as well. Okay. For now, since the DTM is malfunctioning, we'll leave it as it is. So now my source material has been subjected to 35 milliamps for about a minute, and I can see that my source is red hot. The crucible has become red hot. That means the vapors are coming out. The aluminum vapors are coming out. But since I have my shutter closed, the deposition is not happening right now. So we will be depositing for 10 minutes. So I'll just turn on the shutter and start the stopwatch. So meanwhile I'll also keep on checking if there is any deposition happening or not, and because even though it's inside the chamber, due to the e-beam and due to the glowing of the source material, there is sufficient illumination that you can see on your sample whether it is coated with some material or not. Okay, I'll be constantly waving it through the viewport, and once we are done for a deposition of 10 minutes, we will continue. So now it has been almost 10 minutes. As soon as I hit the 10-minute mark, I'll be closing off the shutter, so that exactly at 10 minutes my deposition will stop. Then, okay, it is okay. Now it has been 10 minutes. I've closed the shutter, the deposition has stopped. Meanwhile, the rotation is still going on, and the electron beam is still falling on my source material. So, and it is still evaporating. So what I'll do is slowly I'll reduce the current, and once it reaches 0, yeah, I'll turn off the gun first. So you'll see that from 5 kV it goes to 0. Once that goes to 0, I'll also turn off the power to this panel. That's done. And I'll also turn off the power to the turret controller, which I use to change my material, which I use to switch between my 4 crucibles. Now I'll also turn off the rotary drive. And finally, it is time to take out the sample. But before that, we must also know that because this electron beam is falling on my source material and it is evaporating, the chamber temperature is also a little high. So immediately if I take out my sample, there might the samples might still be hot, and it is quite possible that because of some ambient air, there might be some reaction. So what I'll do, before taking out my sample, I'll just seal and start the cycle. So probably for about a minute or 2, I'll keep it on cycle. When the temperature comes back to normal, I'll vent out the chamber and take out my sample. Now, after the deposition, after turning off the current, the e-beam, we have been cycling it for around 5 minutes, and we can also sense that the chamber has cooled down now. So the next thing I'll be doing is venting it out, venting my chamber. So if you can hear, there will be a slight hissing sound, which indicates that atmospheric air is going inside the chamber. Now once the venting is stopped, and my chamber reaches atmospheric pressure, it will be safe to open it and will be taking out the sample. So now the hissing sound has stopped, and we can also see that the chamber pressure is equal to 10 to the power plus 3 millibars. That is the atmospheric pressure. So we'll just try and open it. Okay. Now you can see the chamber here. I'll be carefully unloading this substrate holder. And again closing it. Now you can see this is the substrate holder, and here we have a glass slide which was actually transparent when we started, and now it is coated with aluminum, and you can see that mirror like shiny finish on top of it. So once I have closed the chamber, now the next step would be to ensure that it is always in evacuated condition. So what happens is, if my chamber is exposed to the atmosphere for a very longer period of time, it might absorb some gases, some particles. So what happens is, when it is kept in such an atmospheric condition for a very long time, so the next time when I'll try to create a vacuum, it will take a very longer time. So it is a good practice that once your deposition is done, keep it, if not at a very high vacuum, but at a moderate vacuum, let's say 10 to the power minus 3 millibars. So next thing I'll keep it on cycle. And now you can see the pump started running, and there is a noise. There is this noise because of this evacuation, which will die down eventually. A fun fact is that this noise dies down eventually is because the chamber is going into vacuum, and in vacuum sound waves cannot travel very well. So that's it for today. Thank you.
I hope you like the lab lecture, and if you have any questions, always you are free to ask us through NPTEL forum. Thank you.